Okay, let's start. So we're starting with what? Surprise! You need to give this. Yeah, he's going to do it. So this is I wanted something that I owe you from last time, showing there's a difference between procedural and declarative learning. So remember the story of HM. He couldn't remember anything in terms of recognizing people and things like that, things that are declarative. But then when Brenda Milner tried doing tasks in which he required just to do things like tracking a star, he improved the cross data. So here's the demonstration. So we all go over the lines of the star just regularly, fast. So you can do it very easily. Now I'm switching the association between your movement and what is actually happening. Now try to follow. So I just turned around the mouse. And you can see it's much harder. Okay? Thank you. I can have a little bit more light. Okay, that was it. And you can try it, of course, at home. All you need is a mouse and that. Okay. So let's start. Any questions, problems with the course, questions about the course? Okay. So what's left? So this part of the course is about motor systems, and we're now we started with the introduction, where are some concepts, some basic facts about muscles and reflexes. I'll talk today and on Sunday on the motor cortex and the spinal cord. So you see it here, and you see here the spinal cord. So this year is a funny year. It turns out I'm teaching you all what other people were teaching in the past. So this part of the course was given before by Fruit, and you can find that on the internet if you want. This is not exactly what I do in my lab, but it's strongly related. So I have my perspective about it. So that will be today and on Sunday. Then Thursday we're having students giving talk about. This is I chose the students talk to be just in a sense a modern continuation of what I'm teaching. So the talk today and Sunday will be a lot about what does the motor cortex encode, and I'll give you all the historical perspective, and the two papers that I gave you are related to a modern perspective of what does the motor cortex encode, how does it do it. So that will be this part. Afterwards, Yossi Aron will talk about the cerebellum. You see it here. Strongly related to the motor cortex, strongly related to movement, direct projection. And then afterwards, Hagai Bergman will talk about the basal ganglia that you see here. Again, strongly related to motor cortex and cerebellum. All these structures are extremely important for driving movement. Any damage to each of these structures will cause a problem with the movement. Again, they're usually studied separately. There's not a lot of work that studies many of them together. So perhaps it will be your job to do the integration across the different approaches that you will hear. Part of your scientific training is to do that. You hear a lot of things from different perspectives, and you're trying to integrate something for your own consistent view of the world. So these are the circuits. I'll talk about this part, again, connected to the basal ganglia and cerebellum. There are also connection back through the thalamus, important motor center, back to the frontal cortex, and also from all these structures, there are projections to the brainstem, to the spinal cord to do movement. Okay. So so I'm talking now about the motor cortex. So for understanding the motor cortex, we want to also understand how it controls the movement. So I'll start by talking a little bit. I talked about it, about the organization of the spinal cord. This is what is the final motor pathway that drives the movement. I'll talk about inputs and outputs of the motor cortex. I'll talk about cortical maps, how the cortex is organized in maps that control different parts of the body. Um, this will be more anatomical and less functional part. Then I'll talk most of the, I don't know, but a lot of part, a major part will be about what do the single neurons say in the motor cortex, what are actually what's coded in the activity of single neurons in the motor cortex. Um, I'll talk about population coding. Georgopoulos, did anybody hear the name? You will hear it again. Those who did. And I'll talk a little bit about more modern approaches. For example, the brain-machine interface, how we can use the activity in the motor cortex in order to help people with disabilities, and also talk about some, let's say, cognitive roles of the motor cortex, whatever that means, but let's say non-direct motor components of the motor cortex. Okay, so where is the motor cortex and how is it organized in a very large scale? So here you can see a brain of a human, a brain of a monkey, and there are a lot of homology between the motor areas. So there are let's say three main divisions. This, I don't know what these colors are. This kind of green is the primary motor cortex, also called the M1, right? We have here the premotor cortex, this is what you see here, and the supplementary motor area, this is what you see in this dark green. This is in the human brain. The motor cortex, you see this is the central sulcus, the motor cortex is just before it. What's on the other side? Exactly, okay. And here you can see it in the monkey brain. There's slightly more divisions. It doesn't mean that these don't exist here, but here they're studied in more detail because of all the experimental manipulations that we can do that we cannot do in the humans. So this is again M1. You see the similarity. The central sulcus. You see the M1. The primary motor cortex, the premotor cortex is divided in monkeys here to two: the dorsal part and the ventral part, which have perhaps slightly different roles. And then there are even higher order areas, F5 and the pre-PMD. This is this area, and you see the supplementary motor area here. So this is a really general organization. I'll talk mainly about this part, about the M1. This is the area that's most close to the behavior, where the stimulations in this area cause the weakest stimulation cause a strong movement already. We know, I'll talk a lot about the projections, but many projections from this area go to the motor areas of the spinal cord. So that's a very general organization. I'll start with, I don't think I talked about this last time, but I think it's a leftover about terminology that we will use in terms of muscles. Do you know this? Did you hear it? Anatomy? No? Yes? Okay. So first, in each movement that we do, we can think about the agonist muscle and antagonist muscle. So in this case, when I'm moving my hand like this, so this is the muscle that's actually causing the movement. This is the agonist, and this is the antagonist, which will we need this muscle to be not active or inhibit it in order for the movement to happen. This movement to happen, and it's functionally based. So in this movement, this is the agonist and this is the antagonist because we're trying to bend the hand. If we're trying to extend it like here, then it's opposite. Then this is the agonist and this is the antagonist. So this in terms of function of what we're trying to do. And then another terminology is in terms of joint coordinates. Is the hand being extended or flexed? So this will be flexion, and this will be in this case the flexor, the muscle that will flex the hand, and this will be the extensor because it will be the opposite thing, will extend the hand. Okay, just terminology, not something very sophisticated, just so we'll have common language. Okay. So, as you know, the cortex is really important, but it needs to tell someone what to do, and that's the spinal cord. Did you learn about this in the anatomy course? A little bit. A lot? not at all. Okay, so I'll remind you. I'm not going into there. You can have a whole course about spinal cord organization. I'm just telling you the general principle. So there are all these segments, different segments of bones, and each of them there's nerves. You can see here the dorsal root ganglia where the sensory input goes, and you can see this enlargement. This is the ganglion, and you can see the nerve entrance into the spinal cord, and you can see here all the spinal cord. It's divided into different parts: cervical, thoracic, lumbar, sacral, and I can't pronounce this this part. And you can see how these different areas, these different segments in the spinal cord, which area they're controlling, and which area they get input from. Okay, so this is just so the cervical are important for the neck and this part of the hand. Then we go to the thoracic. They're you can see in charge of these red parts, and then as you go down also in the segments in the spinal cord. So that's the general organization. Just more a micro spinal cord organization. So this is just one slice of the spinal cord. There's the dorsal part. This part. This is more the sensory part of the spinal cord. There's the ventral horn. This part. This is the motor part. I'll talk about this more, but this is the gray matter in the middle. There's also white matter all around. This is what you see here. And there are different pathways in the white matter. I'll talk about this a little bit more later. So there are two important, there are many important organization principles, two that I've mentioned here. The first is that the spinal cord, and you saw that before, it's related to where the location in the spinal cord is related to where it's actually innervating and controlling the body. It's not that this segment is controlling the leg. It's controlling. It's near the neck, and it's controlling the neck. Okay, that's one simple organization. A more or less obvious one is the internal organization of the spinal cord. So you can see here this hand. This is supposed to represent where the general area in the spine and the ventral horn, which is controlling the different muscles. So when we're looking at this part, this area of the ventral horn is controlling more the distal muscles, the edge of the hand, and as you go towards the center, you control more and more proximal things that are closer to you, the trunk of the body. So that's another principle of organization. So this is simple, important details. We talked about reflexes last time. So we mentioned the stretch reflex, and again, these are just two examples to show the principle. There are many other reflexes that are happening. So these are the simplest motor behaviors, and we talked about this, the stretch reflex, and we even exemplified it. So just to remind you, when you stretch the muscle, the spindle starts to fire. The sensory neurons in the spindle start to fire. They innervate directly the motor neurons, which cause the extension of the leg through this muscle, and the flexor muscle is inhibited. And that's what you see through this interneuron. So this is one example of reflex. This is the reflex in which the extensor muscle was activated. We can think about reflexes where the flexion muscle is activated. So this is the flexion withdrawal. Also has some functional importance. We talked about stepping a nail, or when you're activating your nociceptive receptors. There's a different reflex that is activated, and this is from Kadila-Schwarz. So they wanted, I think, to show you that although you stimulate very, very close areas, here I'm stimulating here, and here I'm stimulating here. They're actually causing different kind of reflexes because I'm activating different kind of sensory inputs. So here, didn't hurt, I hope. When you use the hammer, and then the cause for the reflex is the sensory input in the spindle. Here I'm actually activating the nociceptors, and they're innervated in different ways, and because of that they activate different reflex pathways. So here you can see in this case the sensory input is nociceptive fiber that goes into the spinal cord, and you remember the VOR reflex? It's very similar. Here it's very similar in the sense that we need to do something on one side and we need to do something also on the other side. So we have both ipsilateral pathways that need to activate one muscle and inhibit the other muscle, and the other side we need to do the opposite thing. So the idea here is that I activate this neuron, means that something nauseous was detected, and they don't want to I want to move the leg as fast as possible. So moving the leg in this case means just extending and flexing it or bending it away in this case. So we want to activate the flexor muscle and inactivate the extensor muscle. So we do that through this pathway. One difference between this reflex and this reflex is that here there's a direct connection, you see, between the sensor and motor. Here there's the interneuron. This is more like what we saw in the VOR. So we have here an interneuron that activates, that leads to activation of the extensor, and we have here an inhibitory interneuron that causes this motor neuron not to fire. So why do we also want to activate the other side? Balance, yeah, exactly, not to fall. We want we want to now stand on one leg. So again, there are pathways that pass through in the spinal cord in order to activate the extensor on the other side and inhibit the flexor. So the leg will stay straight. Okay, so that's why you don't fall when you step on a nail. And that's how you move your leg as fast as possible, even without a cortical processing. Okay, so there are there's always these internal pathways. There's also pathways that control them, and this is what will be the main part of the talk. These are the pathways, descending pathways from the cortex to the spinal cord. There are also ascending pathways, of course, all the sensory information that you get from the body you want to bring to the cortex, but I will not talk about that at all, this part. So in red here you can see the descending pathway, the pathway that go from above the spinal cord into the spinal cord that allow you to move and control your reflexes and control the world. So these are in red, and this is all white matter. All this colored this is white matter. These are axons that's going from down top and from top down. They're divided here into two tracks. The pyramidal track, which I'll talk a lot about a lot. These are fibers that come directly from the cortex and from the red nucleus. In humans, I'll talk about it more. In humans, the red nucleus doesn't have a major role. It's mainly a pathway that comes from the cortex, humans and monkeys. So that's all these parts. See that? And there are also many other pathways that control the spinal cord. These are what's called extrapyramidal tract. And pyramidal is the place. The pyramid is a structure in the brainstem where these fibers pass through. That's why they're called pyramidal and extrapyramidal. And at least initially, it was thought that the pyramidal tract is all our voluntary control is done through pyramidal tract, and all the extrapyramidal tract is maybe for more reflexive or higher reflexive, whatever that means. Now we know that you have everything everywhere. But the directest way of the cortex to control the behavior is through the pyramidal tract. And again, there's the organization for the different segments. From the different segments, the pathways go through different places here. So these are the descending pathways that go into the spinal cord. So where do they come from? This is the source of the descending pathways. You can see them here. So these are the different sources that go down the pathways that we see here. See it? So we'll talk a lot about these red cells. This is the corticospinal pathway, the pathway that goes from the cortex, we'll show where it comes from, goes down to the spinal cord for direct control of the cortex, for all your voluntary movement. But this is not the only way the cortex influences behavior. The cortex is also influencing the other pathways. It can control the sources that come from the other pathways and what pathways are these. So this is the red nucleus. Did some dissections, right? Did you see the red nucleus? Did you see the brainstem? So this is it's very easy to detect in dissection. Actually, in humans and monkeys, as I said, it's not as important. In other mammals, it's a more important pathway. And for primates, the main pathway, the corticospinal pathway, is the main pathway in which it controls. We control the spinal cord from the cortex directly. But the red nucleus leads to a pathway that goes together with the spinal cord pathway to make the pyramidal tract. So both of these are the pyramidal tract. Go down in the pyramidal tract, and just the pyramids, which I think are here in the brainstem. So we have also other pathways. Superior colliculus. Did you hear about superior colliculus? Very important structure for orienting behavior, for example. So there's a pathway from the superior colliculus downstream. It's important for controlling head movements, for example, or neck muscles. So, for example, if you hear something very strong, and then you move your head, that's the kind of things that the superior colliculus will. That's the kind of ways that the superior colliculus will control the world. So, orienting your body towards something, either auditory or visual information. So the superior colliculus has it's a very, very interesting structure. It's like a mini brain that has all you need in order to control behavior. It gets a visual input, has visual layers, and then it has deep motor layers. So these are neurons that go from the deep layers of the superior colliculus. And here, that's this. Let's see what else do I have here. Okay, so there are these two pathways that are in the pontine and the medullary, the reticular formation pathways. These control things like locomotion and balance. Very important for that. And there's the vestibular spinal. You remember we talked about the VOR. So the VOR is one kind of reflex where the vestibular input influences the eye movement. But vestibular input is also just for controlling your movement. And you want the way in which I activate the spinal cord if I put my head like this is different than the way I control my spinal cord if I rotate my head, or my center of mass, for example, is different. So all this information is needed by the spinal cord in order to control balance, for example. And as I said, these are the descending pathways, and you saw where they're going through. And they're organized in a hierarchical way in the sense that we have here the cortex that controls directly, but the cortex here also controls all these pathways. There are pathways from the motor cortex to the superior colliculus, for example, and pathways that allows the cortex both to directly control the behavior, but also control through different areas. Okay, so I'll start talking about the pyramidal tract, mainly about the corticospinal tract, and you can see it here. All the complex behavior, or any kind, the complex and precise behavior that we do, it depends on this pathway. So if you lesion the cortex, if you lesion the pyramidal tract, you can see how very specific like movements where you control things with your finger or grasp things that need fine control are damaged. So here's the anatomy. So this is like a motor cortex, and you see the pathway that goes through the internal capsule, and then they connect directly to the brainstem. As I said, I'll talk mainly about the spinal cord, but we saw also for example, in the VOR, that the brainstem is also the motor center for all the face movements and the eye movements. So it's also it's a different. It's not the spinal cord because it's not controlling the muscles that are controlled by the spinal cord, but it also is a motor center. And they have motor nuclei, and if you learned about the cranial nerves, many of them are the nerves that actually are the nerves and the pathways in which control the muscle. So it goes to the spinal cord, and then it goes to the pyramid, and here there are two parts. Most of the cells go to the other side. Go from the one side to the other, so there's a crossing here, but some stay on the ipsilateral side, and that's what you see here. And then this pathway I'll show you later where it converges, but it goes to the spinal cord. in primates and developed primates, it also controls directly the motor neurons. So there are connections, cortico-motor neuron connections from this pathway from the cortex directly to the motor neurons, and I'll show them in a minute, some more of them. Okay, let's see. Anything else I wanted to say? So this is, although this pathway is very important, and maybe this is the pathway that we know most about because we have some experimental ways to actually probe neurons here, it's only 5% of the pathway from the cortex to the spinal cord. So 95% is indirect. So 95% of what the cortex is doing is not going towards, is not activating this pathway, but through other pathways that we talked before. The reason and the experimental reason that we know, first it's the direct connection make it very, very important, but the experimental reason we know a lot about this is that we can, for example, put a stimulation electrode here, activate this pathway, and record neural activity in M1. And this is a technique that was used in the last 50 years. So we stimulate here, the neurons here are activated, right? The action potential goes backwards. And then when you record here, you see a very short activation of the cell. So you record here a cell, and then you know that you're in a cell that's going in this pathway, and you can then go and study its properties to understand what is the motor cortex telling the downstream areas in this specific pathway. So this is called antidromic stimulation. Did you hear about that? Good. So it's only 5% or 95% that comes from somewhere else, and only even this pathway doesn't all go to the motor neurons. A large part of this pathway actually goes to the interneurons in the spinal cord. Doesn't go directly to the motor centers, but many go to the interneurons. And there's additional processing in the spinal cord. It's not that the cortex tells exactly the muscle what to do. It tells the spinal cord something, and the big question, what is the something that it tells it? And then the spinal cord does some additional computation in order to actually drive the movement. That's in the spinal cord, and as I said, there are also many connections from the motor cortex to other non-pyramidal pathways that drive movement through all the other pathways that I talked about. So we will focus on the pyramidal tract, and the question is where in the cortex does the pyramidal tract originate from? So here you can see a picture of the cortex. You can see in red is the somatosensory. This kind of blue is the primary motor cortex, M1, and this is the premotor cortex. And you can see here in the color coded. So this is the cortex, and this is where this is the segments in the spinal cord where they converge on. So first you see that from the somatosensory cortex, information goes to this area. What is this? Which part? The dorsal, right? And the idea here is that the cortex already controls the input to the spinal cord. And this is a way, for example, in which you can control the gain of the reflexes, right? Or control what's going into the brain. So, for example, if we don't want the stretch reflex to be activated, or parts of the reflexes, we can go here and already control at this level what's going into the spinal cord and also what's going into the brain. Let's say we're moving our hands, and there's all the sensory input that's coming because we're moving our hand, and we want to ignore it. This is a mechanism by which we can directly control the sensory input to our brain, and maybe perhaps that way we can inhibit things that we don't care about, that we know that are happening. Okay, so that's the sensory cortex. There is the premotor cortex, this area that goes, you can see here, that goes more intermediate layers, but also goes more frontal areas. That's what you see here. And the motor cortex, as you can see here, goes to the ventral part, but also to the intermediate part. So it has direct access, and I'll show an example in a second, to the ventral part, but it also has access to these intermediate parts in order, so it doesn't have to control only the muscle activity itself or only the motor neuron. It can control in a higher level the activity in the spinal cord. So 60% come from the frontal lobe, but 40% come from parietal, for example, as you can see here in the sensory area, in the pyramidal tract. So we think of it, we think of it as the motor pathway. It's not just a motor pathway, or for sure not a direct motor pathway. And then we have 75%, most of it is contralateral, crossing from one side to the other side, but there's also 25% ipsilateral. So it's not that it's only controlled the other side of it's not that only the right motor cortex controls the left hand, but it also, there is some ipsilateral connection. Okay? And often you hear people say, well, the right brain is controlling on the left part. Things are a little bit more complicated for that. And in the brain, mostly, if there are these effects, mostly they might not be very functionally important, but then when you do these perturbations, these pathways could become even more important. So the brain is more complicated in our cartoons. So something that happened in evolution. So originally the pyramidal pathway was mainly for controlling the sensory parts, and here you can see different kinds of animals and where the fibers in the cortical spinal terminate. So this is the opossum. I should have bring a picture. Does everyone know what the opossum is? Okay, good. So you see that the termination of the spinal tract is mainly in the dorsal part. That's what you see here. In cats, you see that now it's in the cat. This is from, I think, M1. Yeah, from the motor cortex. In cats, you see that now it goes to the intermediate segment, and then when you look at monkeys, rhesus monkeys, it's starting to go also to the ventral part, and then in chimpanzees, it's controlling both the ventral and the intermediate parts of both ventral and intermediate parts of the spinal cord. So we see this shift from dorsal to ventral control of the spinal cord. And as I said, the sensory parts are for gating motor. You can use this to gate the sensory input if you want to control your reflex, for example, or control what the input the brain is getting. Okay, so this is a nice example, one of the first examples of people showing. Okay, we have this cortical pathway. How does a single neuron affect the motor centers in the spinal cord? And you can think about many different possibilities. One possibility is that there's each cell in the cortex will activate a specific pool of neurons in the spinal cord to control a single muscle. That could have been the possibility. But what they found is something very different. So here you can see one neuron. Here you can see a neuron coming from the cortical spinal tract, going in the places where the cortical spinal tract is supposed to go. And you can see here the termination, so you see it going, and each of these is a different motor pool that's controlling a different muscle. And you can see that the same neuron is connected in many, many pools. So that tells us that it's not that the motor control is single muscle based, it's actually controlling more complicated behavior, a combination of different activation of different muscles, which is the kind of activity that we need in order to actually move in the world. And another thing that it's harder to see from here, but the same fiber can activate both motor pools, but also interneurons. So it's not that has even the single. There are many fibers that go only to interneurons, but even the fibers that go to motor neurons could also activate interneurons. Again, this means that the type of message the cortex could tell the spinal cord could be more complicated than a simple move this muscle or even move this group of muscles, but maybe do something more adaptive and complicated.
But usually these groups of muscles are they're near each other.
They're near each other. They don't. So the term of is a muscle antagonist or agonist depends on the movement itself. So the same muscle for different movement could be once, they could be antagonist muscles, but in other movement they could work together. So it depends on many things, right? So I can, if I do this kind of movement and now try to move my hand, it will be different than I do this posture. But they are, it's organized in segmental way, so the segments are controlling near muscle. They can also, maybe related to your question, they can also innervate different segments. So there could be a neuron that's connected through segments and then activating muscles across segments, which could be more distant muscles. Okay, so that's how the motor cortex, these are the pathways the motor cortex could control behavior. The motor cortex also gets a lot of input, obviously. It needs, and you can imagine, it needs sensory input, it needs context input, what's happening in the world. Different situations would want to do different kinds of movements. And it gets it all the time. It's not that the motor cortex is waiting and doing nothing. It's all the time integrating all the sensory input and all the cognitive ideas that you have in order to drive movement. And it's doing it from multiple sources, right? It's getting it from cortical, subcortical areas. And we need to do everything in a task related, right? It depends on what we're trying to do. And in the, you look at something, you see a snake, you want to run away, and the other hand you see, I don't know, $100, maybe you want to approach. So your behavior is task dependent, obviously, and the motor cortex needs to be task related. So that's in terms of the input. It's not that there's very discrete, simple inputs. It's something that it's a dynamical system that works all the time in order to drive behavior. And here are the subcortical connections. So there's these words that are next to each area. Each time you see functional words next to area, you should be very cautious. Often it's more the imagination of the or the conception of the science, but not always very strongly with proven with a very precise science. So these are ideas, so the idea is here that we have the cortex. It talks with, this is the thalamus, and there are areas in the thalamus that the cortex sends projection. And there are two kinds of loops here. There's the loop through the basal ganglia. This is what you see here. And basal ganglia is often blamed to be related to motivation, action selection, habits. So this is way, and I'm saying again with a lot of caution, in which the cortex could control the basal ganglia or send information to the basal ganglia in order to get that information about action selection or motivation. Practically, you do see basal ganglia is important for motivation. There's no doubt about that, but it's not that the segregation between motivation only in the basal ganglia and cortex being not related to motivation is probably not true. Or I would say differently, there is not strong evidence that show that. So this is, but in terms of pathways they exist, we know that the cortex is strongly connected to the basal ganglia, and through the thalamus the cortex gets information back, but there's also a loop here from the cortex to the thalamus and back. And the critical question is what's happening in this? We have this nice organization. What is the information that's going here? What is the information that's going here? We have a lot of ideas. We don't have a lot of real strong evidence for these ideas. So this is one motor loop. Another motor loop that for subcortical input is through the cerebellum. The cerebellum gets strong input from the sensory spinal cord. And also, as I said, input from the cortex, direct input from the cortex. And again, it's a loop, so it sends back information through slightly different areas in the thalamus that go to the cortex. And again, the cortex controls these areas directly. So you see this big loop that goes through these areas, and also this short loop that goes through the direction that are controlled by the subcortical loop, which is interesting organization. The cerebellum is blamed to be related to error signaling, for example, when you do something wrong, when you do some behavior, you miss the target and you want to correct your and you want to correct your movement, so the cerebellum is often blamed for doing that. Again, this is probably true in some sense, but probably not only the cerebellum is doing error correction. As I said, the sensory input gets the cerebellum, so it's also a way, a pathway that the sensory input goes back to the cortex. So these are the subcortical inputs to the motor cortex. There are also cortical inputs, and here again they're somewhat organized hierarchically. So here you can see again the motor cortex. This is again in a human in this case. Again, for some reason they like weird green colors in motor cortex drawing. So this is the primary, this is the premotor cortex and supplementary cortex. There are connections inside the cortex, and generally, and this is a general principle, but again, there's exceptions for this. These are higher motor areas that control higher kinds of behavior, and like contextual things will be more related to here, and we'll show some examples. And the primary motor cortex will be more related to the actual details of the movement. So there's these connections from premotor and supplementary motor towards the motor cortex, but there's also connections from different areas. So this is a sensory area. It's connected strongly to the M1. Again, because all our movements, in each movement we do, there's all the time sensory information, which is crucial for us, and we want to use it for actually generating in the way we generate the movement. There are parietal areas that are related to our movements, reach areas in the parietal cortex. You see them here. They're mostly not connected directly to the motor cortex, but connected to the what we call higher motor areas, so the supplementing the premotor. So there is some kind of hierarchy here. And the premotor is the area that is, on one hand, we know there are many areas that are related to the our movement itself, but it's also a visual, it also gets strong input from the visual areas. So this is the area where visual information is used in order to guide the hand movement. Things we can think about, things of where I'm looking at something related to my body, for example, and I want to locate it, and and the neurons in these areas will be related to this kind. So if I do a movement towards a specific object or a specific area related to my body and what I'm seeing. So these are the kind of representation that you'll see here. But again, this is not a direct motor area, because the way which controls behavior is through these projections to the motor cortex and then to M1. So that's the cortical organization. And now let's see what the time is. Maybe after the break, we'll talk about the maps in the motor cortex and actually go into the details of the first stimulation in the motor cortex, what it does, and then the details of the activity of the motor cortex. Questions? So let's come back at 10 o'clock and we'll continue.
אמנם כאילו, אני יודעת שזה שלי.
אוי, לא הצלחתי לזה.
אוי.
תקשיבו לי שזה יפת.
יש לנו כמה שאלות, אנחנו לא מצליחים לראות אותו במייל.
לא צריכים לתפוס את יופי במייל?
כן.
זה המשרד שלו. המשרד שלו בקומה שלישית פה. קומה שלישית יש שם איתו בדיוק ליד. בסדר? ואם אתם לא מצליחים עדיין, אז אני מכין את שתי המאמרים שלו. אם הוא לא מוכן לדבר איתכם, אני יכול לדבר איתכם.
לא, נראה לי שהוא ישמח לדבר.
הוא פשוט צריך לתפוס.
לא, אני מכירה אותו, כן. תודה.
בסדר?
ברקודים שאני אנשים, הם עושים לנו טראג'קטורי, ראיתי, קראתי איפה גם כן, שיש את הצד של דיקומפוזישן, כאילו כמו שאתה...
מה הם עושים?
כאילו, אני לא יודע אם זה משהו אחר, זה רקודים של EMG.
EMG בשריר אחד,
מה זה כל טראג'קטורי כאן? מה זה מייצג כל אחד מהם?
שאלה יפה, אני לא יודע. בדרך כלל זה התנועות ידיים, נכון? פה זה לא הגיוני.
זה פעילות כאילו חשמלית. פה זה התנועות ידיים, זה הפעילות החשמלית.
זה הפעילות החשמלית. אז זה כן, למה תנועות ידיים? כי במקרה הם בחרו דעת שיש תנועות הרבה קרב יותר. כן. זה לא הכרחי, כן. במקרה, אוקיי. זה אני מבין, זה ה-EMG, כן.
ב-EMG בתוכו, מה כל קו מייצג?
הם מעצבנים כי הם שניהם רק...
ראיתי, לא יודעת לשים את זה כאן.
זה EMG ברמה אחרת. זה EMG, אני חושב שאתה מסתכל, הם לא עושים EMG שאתה מסתכל על סיבים בודדים. אז השריר מורכב זה נראה לי סוג אחר של רישום EMG. אז כמו שאתה יכול לרשום תא בודד, אתה יכול לרשום סביב שריר בודד.
כן.
או מעט סביבי שריר, בזה שאתה תשים את האלקטרודה ליד אלקטרודה חדה, כמו שאתה יכול לרשום...
מולטי-יוניט,
כן,
אבל סיבים.
בדיוק, בסיבים, אבל בדרך זה לא מה שהם עושים, הם שמים איזושהי אלקטרודה מאוד גדולה שמכסה באיזשהו מובן מייצגת את האוכלוסייה, כמו LSP כזה.
אוקיי.
אז אם אתה יודע, יש לך שריר, אתה יכול, יש פה המון סיבים, זה לא שאפשר לרשום מסיב בודד, אני חושב שזה מה שאתה ראית שם, שאתה יכול לשים איזושהי אלקטרודה הרבה יותר גסה, שתרשום פשוט.
ואז מה כל קו מייצג? הם עושים איזשהו כאילו דיקונסטרקשן של הדאטה.
זה קו מייצג את המתח החשמלי.
הכללי.
כן, הכללי של הזה, זה כאילו, זה מתח, זה כמו LSP בעיקרון. זה מה שאני מנחש, תבדוק את זה במתוד, אני יותר לעצמי, אני די בטוח. ולעשות גם זה מאוד קשה לעשות את הניסוי של שריר זז. לשים אלקטרודה חדה ליד סביב שריר, בניסוי שחייב מתנהגת, זה לא משהו שאני מכיר מישהו שעושה.
רוצה להסתכל על המצגת, או שבניס בינתיים?
אוקיי.
אז מתחילים
זה יהיה,
להסביר.
זה אני אציג את זה בשבוע הבא.
אז מסבירים כאילו מה זה אומר הפונקציה הזאת, מה זה פונקציה דינמית, ואחר כך ניכנס באמת מה זה אומר.
מה זה פונקציה דינמית? כן.
שזה איך זה פועל, כאילו שיש לך state space, ששם יש לך אותו חוקים לכל הטראג'קטורי, זה כל השאלה איך הם מתחילים.
כן.
אז דוגמה ממש יפה לכזה, עוד דוגמה ממש כאילו יפה, זה במקרה של מוטור קורטקס, במוטור קורטקס כתוב ממש די מוסכם שב-V1 יש לנו איזשהו טיונינג פרמטר, כאילו פונקציה כזאת, כמו שהיינו בהתחלה, פונקציה של פרמטר, שזה פונקציה של כאילו
כן, הם כותבים את זה?
מתאים מסוימים.
כן. לא, אתה אומר יש טיונינג לפרמטר.
כן, יש לנו ב-V1 מקרים ממש כאילו ברורים של טיונינג פרמטרים, שזה בדיוק הניסויים האלה של
מה שאתה אומר עכשיו, אני תוהה אם מישהו באמת ניסה לעשות את זה. עכשיו קח את הגישה שלהם לעשות את ה-V1, תוך שיש שם דינמיקות שהן לא טריוויאליות. יש לך און ואוף ואון-אוף במקומות שונים, אני בטוח שאם קצת תרצה, אתה תכניס תחילה למצוא את זה שתרצה. כן.
ואז לקחתי פה מקרה של ה-velocity מודל שלהם, ואיך זה נראה במקרה של הקורטקס. כאילו זה ההבדל פה באמפליטודות, זה בדיוק ההבדל שאנחנו היינו מצפים לראות.
למה יש velocity לפני ה-movement onset?
מה?
למה יש velocity לפני ה-movement onset?
לא, זה לא velocity, זה ה-velocity מודל. זה כאילו הם עשו מודל שאם המוטור קורטקס היה עובד בצורה כזאת,
כן, אבל ה-velocity
הוא נראה.
פה, אין velocity. למה יש activity בלי velocity?
זה לא רק תלוי ב-velocity, זה תלוי
אין תנועה, אין קינמטיקה, על פניו. יש EMG לפני, אבל... אוקיי, לא משנה, אני שואל, אבל בסדר. לא קרה, עוד זה לא קרה.
כאילו הם עשו כאלה, אני לא יודע, אוקיי. מה? זה לא velocity כאן, זה לא אמור להיות check velocity כאן. זה מודל שהם פיתחו, לקחת את זה בקטע יותר מאוחר של המאמר.
כן.
הם אמרו שאם המוטור קורטקס היה עובד בצורה שהיא direction סלקטיבית, ככה היה דאטה נראה מנוירון בודד.
יש, אבל מה שאני אומר שיש פה איזשהו משהו שאני חסר, זה להבין למה יש, זה לא רק velocity, יש שם איזשהו, ה-preparatory activity פה.
הם עשו קליברציה לכל הפעילות לבייסליין,
הבנתי. אז ה-preparatory activity מתאר את ה-velocity שיקרה אחרי זה.
כן.
אוקיי.
כן. שבמקרה הזה אנחנו קוראים קורלציה מושלמת בין
כן, זה לא חוכמה.
ובמוטור קורטקס אני אומר שזה קצת מסובך, לקחת את זה למאמר אחר באינטרנט, שלהראות רק שלכל הכיוונים המסוימים יש לנו דברים שהם לא בכל הדברים יכולים משהו
כן, זה עוד איכשהו, כן, יש לך פה כל מיני כאלה. כן, מקרים מוזרים. אוקיי.
זה מהדאטה שלנו, זה לקחת את זה מהקורס של neural networks, להראות שאם אנחנו מסתכלים על פעילות של נוירונים בודדים, וזה קצת רלוונטי לקורס שלנו.
כן, אין שום בעיה. תיקח בחשבון אבל שלא כולם עושים את הקורס.
כן. מערכות דינמיות.
לא,
אני מנסה להסביר את זה. מערכות דינמיות, אם אנחנו מסתכלים על נוירונים בודדים, אנחנו רואים רעש כזה.
כן.
אבל אם אנחנו מסתכלים על זה בבסיס פעילות אחר, אנחנו רואים פונקשן או משהו ואורדר. וזה מה שהם מנסים לעשות כאן. אז קודם כל...
טוב, חייב להיות מערכות דינמיות, אתה יכול סתם לקחת פעילות ולעבד אותה.
ולקבל פונקציה...
כן, אני אקח, מה זה משנה? לא חייב להיות, אני יכול לקחת...
זה מה שהם מציגים, כאילו זה מה שהם
זה לא, זה דרך, מערכות דינמיות אולי זה יקרה, אוקיי, בסדר. זה דרך לקבל את הדבר הזה, אבל אתה יכול, אני חושב, אתה לא חייב
להגיד שזה דינמי?
לייצר את זה, אני לא חושב שזה הכרחי.
וזה מה שמנסים לעשות במאמר הזה. אז אני מדבר שכאילו, מה שבסופו של דבר אנחנו רוצים לעשות זה להפוך את הדאטה שלנו לפונקציה כזאת. להפוך לקחת את ה-RP, נשים אותו בתוך קבלה כזה, ואז לנסות להסתכל על זה בצורה מוזרה כדי לראות אם יש לנו פונקציה מסוימת יפה. עכשיו יש לנו אין סוף פרמטרים, אין סוף דברים שאנחנו יכולים להתאים כדי להפוך את הפונקציה הזאת לפונקציה כזאת, אז אנחנו צריכים לשאול מין שאלה.
איפה הוא,
כאילו
מרחב של איפה הוא?
הזאת, כאילו מרחב שאנחנו רוצים להסתכל עליו.
קודם כל בחרתי לינארי. יש פה בחירה ללינארי.
כן, זה לינארי. מה שרציתי להגיד זה שיש לנו אין סוף דרכים לעשות את הפונקציה הזאת.
אוקיי.
נכון? ואם אני רוצה לעשות את הפונקציה הזאת, אני צריך לשאול שאלה מסוימת. צריך לראות אם אני הולך למצוא משהו, ומה שאני רוצה לעשות זה למצוא את האוסילציה. למצוא את הרוטיישן של הספייס. לנסות להסביר את הדבר הזה, שלא מצליחים להסביר דרך הגישה הקלאסית. וזה מה שרואים כאן.
כן.
ואז אני אסביר קצת טיפה איך עושים את זה, שקודם כל מה זה PCA, מה זה PCA, מה זה מסתכל על מרחב שבו אנחנו מסבירים את השמות הכי טוב, ואז לקחת את המרחב הזה, לקחת את השש, לא יודע, נגיד לקחת את הששת האייגן וקטור הכי...
טוב, לא בטוח שה-PCA הוא הכי קונספטואלי, אבל בסדר.
ואז אנחנו...
יכול שאפשר יותר על זה.
כן, רציתי להגיד שעושים את הדבר הזה רק כשאנחנו מתרכזים ב-highest magnitude complex eigen values שהם אחראים לראות רוטיישן בפייספייס.
טוב, זה מה זה משפט כזה מסובך עכשיו?
אז כאילו, אני אגיד קודם כל שאנחנו עושים ניתוח
יש שני דברים, יש את הצורה שבה הם משתמשו ב-PCA ויש PCA בתור אנלוגיה. מה זה JPC, איך שהם משתמשו ב-PCA זה קונספטואלי, זה לא קריטי, נכון? כי אמרנו, תסתכל על 6, תסתכל על 100, אתה יכול לקבל את אותו דבר בעצם. בתור אנלוגיה ל-PCA תשתמש בזה רק עם זה יעיל, אנשים יודעים מה זה PCA. אתה מבין מה אני אומר?
כן.
כי יש פה קפיצה, יש פה, אתה אמרת המון דברים שחלקם קריטיים וחלקם יכולים לעזור. חלקם יכולים לעזור את חלקם. בסדר?
אז בגדול, מה שרציתי להציג בגדול זה כמו שאנחנו עושים PCA רק ל-eigen values, אנחנו מין כאילו עושים PCA כדי למצוא את הבסיס שנותן לנו את המרחב עם ה-complex eigen values עם הנקודה הכי גדולה.
אתה רוצה להשאיר את זה ישירות עם ה-MSQ וה... להגיד, הנה, במערכת הזאת, בערך יש לי את X דוט שווה ל-MSQ X, וזה גורם לי לסיבובים, ולעומת החלק הסימטרי שזה יגרום לי למתיחות בזה. אולי, אני אומר...
אנחנו רוצים לפצל, כאילו...
כי זה כזה קצת out of the blue, אני חושב. אוקיי.
אז רגע, אמרת שה-M סימטרי, כלומר, זה המערכים העצמיים האמיתיים?
החיוביים, נכון? פונקציה סימטרית כל הערכים העצמיים שלהם. הם ממשיים, נכון?
כן. ואז אנחנו מתרכזים ב-MSQ, מנסים לעשות לו, כאילו אנחנו לוקחים אותו, לא עשינו PCA, אנחנו פוצעים את ה-PCA לשני ילדים, אחד שהוא ממשי ואחד שהוא
לא אמרתי PCA, אני עושה את הפיט לדינמיקה, X דוט שווה X, הפעילות שווה לפעילות כפול M, או M כפול הפעילות.
אז ה-M הזה אני יכול להגיד שיש לנו חלק שהוא ממשי, שזה אחראי ל...
כן. אני חושב, זה פשוט... כי אתה אומר, הכנסת פה, הם משתמשים כל הזמן באנלוגיה הזאת, אני מסכים, של ה-JPC לעומת PCA, שהנה זה מראה על ממדים וזה מראה על ממדים, אבל זה סוג אחר של ממדים, אחד זה ממדים במערכת הדינמית, והשני זה ממדים בלי רגרדת במערכת הדינמית.
וגם משהו ממש חשוב להגיד זה שהששת ה-JPC שיש לנו הם אותו ספייס של
ה-PCA, הבנתי. אתה אומר שזה תופס את רוב הנתונים.
זהו, אז רציתי להגיד PCA, כי אז אני רואה את הוידאו שנמצאים שזה ממש יותר, שמראים כאילו... תמיד חוזר.
כן.
אז כאילו, בהתחלה הם מתחילים עם PCA רגיל, ואז הם מראים לנו איך הולכים את זה ל-JPC, שזה פשוט פליין אחר בתוך ה-PCA. זה רציתי להגיד קצת על
הבנתי.
PCA.
הבנתי.
אולי אני אציג את זה, אם
כן.
אני אפצל את המתודה שלי לסימטריק ולזה,
אולי,
וביטי
אני,
אחר כך ל-HCA.
אתה יודע, תשאל את החברים שלך, הם ידעו הכי טוב מה ברור.
אוקיי.
אולי להם זה יותר ברור.
ואז הקטע של אמיר, שהוא יסביר על...
השקעת המון זמן בטכניקות, רק
זהו,
הקדמה.
זה חשוב לי לדעת כאילו מה אנחנו מסתכלים, כל הדאטה אחר כך מנסה לדבר על ה-rotations האלה, ואז כאילו זה ממש יפה, אבל מה אנחנו רואים פה?
כן.
ואז בסופו של דבר יש להם כמה קנטרולים במודלים שהם עושים
רגע,
כדי...
מה, איפה היית?
הייתי כאן. אז הוא
אוקיי, זה תגובות הן מסובכות.
התגובות הן מסובכות,
כן.
ואז שאנחנו רואים את ה-multiphasic activity, ואז פה יש לנו את הקטע של הוולידציה, שהמערכת שלנו כן מצליחה, שאם אנחנו לוקחים מקרים של ממש אוסילציות ברורות, אנחנו כן רואים רוטציות ממש יפות כאן.
כן.
במקרה שלנו כאן אנחנו כן רואים.
למרות שההתנהגות היא לא אוסילטורית, במובן בקינמטיקה היא לא אוסילטורית, כן.
כן.
למרות זאת, כי הדינמיקה היא כן אוסילטורית בשביל המוח, הכוח, בסדר. אוקיי.
רגע, פה היא כן מסוימת, כאילו פה זה 1.5, זה כאילו ממש אוסילטורי, במקרה הזה זה ריץ', במקרה הזה זה לא ברור מאליו, במקרה האלה זה כאילו ללכת וזה סבבה. אוקיי, אז זה שתי מקרים של ולידציה, זה מקרה של אוקיי, עכשיו זה כן עובד במקרה, זה התוצאה כאילו הראשונה שהם רואים במאמר. ואז הם עושים את זה לכל החופים, לכל מיני סוגים של straight reaches, של curved reaches, ורואים שעם ה-JFC שאנחנו עושים כל פעם לכל אחד מהחופים, אנחנו כן רואים שיש את אותם חוקים. כאילו ברור שהם ילכו שמאלה, כי אנחנו בנינו את זה, אבל כולם הולכים שמאלה. כל אחד מהם, כל הטראג'קטוריז הולכים באותה נקודה.
ומתחילים מאותה נקודה בערך.
זהו, שפה אנחנו רואים פה גרדיאנט ממש יפה שכאילו של הריצ'ז עצמם. יש לנו פה...
כן, לפי הכיוון ולא לפי...
אנחנו רואים כאילו ייצוג של הדירקשן סלקטיבי, איכשהו דירקשן סלקטיבי,
כן,
זה מתחילה. כאילו... וזה משהו גם ממש חשוב להגיד כאן, שמה שהם צריכים לעשות כאן, שהם לא צריכים לעשות בגישה הקלאסית, זה להראות קשר יפה מאוד בין ה-preparative activity ל-movement activity, שאתה לא יכול להיות פה הבדל, אתה לא רואים פה שבירה איפה שהיא, הכל כאילו הולך סמוזלי ממש, הם לא מתעלמים מזה כמו ש...
כן.
אוקיי. ואז נכנסים לטסטינג של המודל, כאילו, מה שרציתי להגיד כאן זה שאנחנו שמים את זה בתוך מרחב שאנחנו גורמים לו, אנחנו חייבים לראות רוטציות איכשהו בדאטה שלנו.
כן.
השאלה שלנו זה אם
יותר מ...
כן, אם אני עכשיו אקח פונקציות, אני ייצור דאטאבייס שהוא מבוסס על זה, ואני אשים אותו ב-JPC, ואני אגיד את הרוטציה. אז המודל הראשון זה ה-Velocity Direction Selective מודל, שזה פשוט בנוי על אוכלוסייה של תאים, של Direction Selectivity, שעשו לזה קליברציה על ה-Firing Rate, Trial Count, Neuron Count, Spiking Noise, אפילו הרעש, הכל היה מותאם, ולא רואים פה משהו ברור מאליו, זה שתי קופים.
יש כאן איזשהו מדד פה לכמה זה טוב?
כן, בסופו של דבר הם עושים
זה ה-MQ, נכון? זה ה-MQ לעומת M.
היה MQ והיה עוד מדד
זה
של
MQ לעומת M, נכון?
כן.
ומדד של זה.
לא שמתי את זה עדיין כאן. למרות שהמדד של הזווית יותר ברור.
כן? לי MQ מאוד ברור. אבל אולי כי הרצתי את זה.
זהו, MQ עדיין לא... יש המדד של הזווית פשוט כ...
הזווית של מה?
של בוא נגיד כאן. זה הזווית, יש להם תמונה ממש טוב, שזה מסתכל שם.
לא בכל. 72, וחצי. עכשיו אני
יש את המקום. שזה כאילו, אנחנו עושים, יש לנו את הקו, יש לנו את הגדרת, הגדרת פה שיהיה בצד הבא, אנחנו חושבים שזה בין הצד הזה לצד הבא, ואנחנו רואים אם הוא הולך שמאל, כמה הוא הולך שמאל. אנחנו יודעים שהוא הולך ללכת שמאלה, ושמאלה כאן זה פאי חלקי 2, וכמה זה שלוש.
פאי חלקי 2 זה ממש
שמאל, כן, רוטציה שמאל. ואם זה ממשיך ככה לא לכל נקודות, אז אנחנו יודעים שיש לנו רוטציה שהיא קבועה. אז זה המודל הראשון, ו-Neural Pathway Facilitation, כמו שאנחנו רואים כאן. והיה עוד מודל שזה Complex Kinematic, שזה מבוסס על ערכים, לא יודע אם להגיד מוטוריים או פוזישן.
לא, איך מוסיף Acceleration Position דבר ראשון. הם לא מחלקים דינמיקה, כי אז זה כבר...
כן.
אני חושב שאין פה דינמיקה. בתנועות עיניים למשל המודל הזה הוא ממש טוב, כי אין הבדל בין קינמטיקה לדינמיקה שם. במקרה בתנועות זה, מה שעושים בדרך כלל אתה רוצה להסתכל מה התאים מגיבים, עזוב את השאלה, אתה פשוט עושה רגרסיה על כל הקינמטיקה שאתה רושם, כל הדינמיקה שאתה רושם, וחלק מהתאים הם קינמטיים וחלק מהתאים הם דינמיים, אני אדבר על זה.
מה זה קינמטיים זה שמגיבים למרחב?
לא, קינמטיקה כן, זה תנועה, דינמיקה זה כוח. אני יכול לחשוב, אני אדבר על זה, לא היום, על דרכים להפריד ביניהם. כלומר, אני יכול להפעיל את אותו כוח, אני יכול לעשות את אותה תנועה, אבל אני יכול לעשות את כוח, לבד מעט כוח. אני יכול לעשות סיטואציה מסוימת. ואז במצב הזה, קינמטיקה היא אותו דבר, אבל הדינמיקה היא שונה. זה על ויכוח שלם, אני מדבר, האם התאים מקודדים קינמטיקה או דינמיקה. גם אתה לוקח את הקינמטיקה עצמה, אז אתה לא מכוון את זה באיזשהו מובן. קינמטיקה יכולה להספיק פה, אתה יודע, ראיתי שיש לך, אני לא יודע מה הם עשו, אבל אם אני יכול לקחת גם נגיד את הוולוסיטי ואת האקסלריישן כמעט הפוך, למשל, ואז אני יכול לקבל נגיד תנועה, נגיד מה שעושים מאוד שהפרופייל של הוולוסיטי שלו הוא קבוע, הפרופייל של האקסלריישן שלו, פשוט הגדרה של הנגזרת של זה, כן? ואם אני לוקח משקלות אחרים, אני יכול לקבל כל מיני דברים פאטרן מאוד מאוד משמעותיים. אני לא יודע איך הם מתמודדות, או אם הם בכלל מתמודדות.
מה שאני נכנסו את זה במאמר?
לא יודע, המודל הקינמטיקה, אני חושב שאפשר לסבך אותו ברמות הדרג'ט, זה הנגזרת שלו.
לא הוכחה, ואז פה זה אבליקנטית בינתיים, של מסל אקטיביטי ובלתי
מה היה הדבר
פה אנחנו מתחילים
מסל, כן. מסל, כן, זה מה שאתה, כן. לא, אז מסל אקטיביטי הוא לא, ואז אתה עושה שיפטים ולגים, אז אתה כן נצליח. שזה נקודה מעניינת. בעצם יש לי תנועה שהקינמטיקה היא נראית מאוד לינארית, בעצם יש שם אוסילציות ברמת השרירים.
כן.
אני יכול לקבל אותם בסיס כזה עם הלגינג וזה, אני לא יודע מה היה המימוש של לגינג במוח.
זהו, אז לא הייתי לתת את האנלוגיה להגיד שיש לי פה שתי נוירונים. כאילו, בוא נגיד במקרה הכי פשוט,
כן, שתי נוירונים, למה? אני לא יודע, כן, אתה צריך לסכום אותם בדילי, משהו שעכשיו, אני לא יודע איך עושים את זה, לא יודע מה האלגוריתם שמציעים לזה, איך המוח יכול לעשות את זה.
אז במקרה הכי פשוט, בוא נגיד שהמוח כן עובד כמו דינמי. בוא נגיד שכל נוירון מייצג איזשהו...
זה מאוד במוטוקורטקס, עכשיו אני צריך לקרוא את זה.
כן, אז יש לנו קשר ישיר בין הנוירונים האלה לשרירים, בוא נראה אנחנו עושים לכל הפעולות בשרירים האלה, דרך הפעילות
הוא לא חייב להיות ישיר, כן. יכול להיות שהלגינג והלדינג הזה מבחינתם, יכול להיות שזה מה שאני ממש בספיילר.
אז זה בוא נגיד שיש לנו פעילות בנוירונים, שאנחנו רואים זה האוסילציה לפני נוירונים, לשתי תדריות. אבל זה בגדול על המהלך הראשוני.
כן, נראה זה. יאללה, בוא נמשיך. אוקיי. בוא נמשיך? Let's continue?
כן, תסגור את זה
Elisheva wanted me to close the door, but... קחי אחריות על מה שאת אומרת, אלישבע. אוקיי. So I know that the microphone was off all last lecture. That means you will not be able to hear me on the internet. And that's encouraging you all to continue and come to all the talks because things like that happen. But if you miss something and you have questions, I'm always available and I'm happy to answer. Okay. So it was mostly, I would say, functional anatomy until now, and now we'll go a little bit more to the function of the areas and what is actually encoded in the different areas in the motor cortex. So it was for a long time the questions, the questions that people had even before we had neuroscience is what is the brain doing and what are the different parts of the brain doing. And there were hints that the motor cortex is important for movement. There were hints from lesions, and even before we had the modern techniques and modern thought of science. My example for a historical hint for how things are organized came from seizures. So there was, when people looked at people, when doctors looked at people with seizures, they noticed that often there's a very organized way in which the seizure happens in terms of the motor effects. And there was one of the doctors called Jackson, he termed that coin Jackson, or on his after him the term was coined Jackson march, where you see how there's, in a very organized way during a seizure, different parts of the body are moving. So initially you can think of the finger moving, and then maybe the arm moves, and then you see how the seizure approaches in the brain. And the thought was that this is reflecting some organization of the cortex, that things that are close in the terms in this functional approach march were also close anatomically in the brain. That was initially, and then later, and here you see a very nice experiment of Sherrington and Layton, where they looked at the brains of monkeys. Actually found this paper. It's really amazing what they did. This is 1916. They did work, and it seems like a paper from 2018 in terms of the organization, in terms of how things are described. Really nice. So what they did is took monkeys and apes, and then stimulated different areas in the cortex, and just mapped. They stimulated and mapped what kind of behavior they saw. And one thing that they did, which is again something that now we understand the functional implications of it, but they didn't just do a huge stimulation. They tried to really be close to the a threshold that will cause movement, and then they just documented what kind of movement they saw. And their initial figures look like this, so it's hard to see. So this is the motor cortex, and there are different numbers here, and it gets to 300, and insane numbers, 373. So at each location, they documented some kind of movement, what they saw, and these movements were complicated. It's not that even the slightest stimulation didn't cause a simple twitch only in the finger, but some caused a twitch in the finger, or maybe something in the mouth. It was relatively complex, and their paper mostly is these kind of documentation of how stimulation at different points causes different types of movement and complex movement. But then they compiled all their information. They came with a map. Okay, and this map, there's a huge, I would say, dimensional reduction between what's happening here and this map, and this is a simplification of what they saw, but they did try to separate it into different, generally different areas, and say that some areas are related more to different body parts, and in a second I'll show more detailed picture of this from later studies. And so these are all hand and arm movements, and it's hard to read, but in this area is the eye area. So we have a cortex for general body movement, and we also have an area that leads to movements of the eye. Later it was called the frontal eye field. Strongly studied in monkeys and even in rodents, although they don't really move their eye. There still is a piece of cortex that is thought to be also control the eye. I'm really interested in this area, but I won't continue to talk about it. I'll continue to talk about the more work about the motor cortex. If you have questions about the frontal eye field, I'll be happy to answer or talk about it. Okay, so the picture that emerged from this is, there is different. The cortex is controlling different parts of the different types of movement, but the map was not very clear. And then later, Penfield and found or described the map in humans, and Weasley described a similar map of movement in monkeys. So Penfield was a neurosurgeon. During his surgeries, he needs to localize. I think that most of these are surgeries of epileptic surgeries, where they need to maybe remove part of the cortex, but they need to map the cortex before they actually do the surgery. And then in order to do that, he stimulates in different areas. So he stimulated in different areas in the motor cortex, and he came with this map where he described that different parts of the motor cortex control different types of movement. As I said, Weasley did the same thing in monkeys. And there are some principles that you can learn here. So like the somatosensory map, there's difference between the size of the organ and the amount of part that controls it or gets input from it in the sense of somatosensory. And that gives us a hint, at least, about what the motor cortex is doing. So you can think one thing that the brain needs to do is also to amplify signals. And you would think that if all the brain is doing, all the motor cortex is doing is amplifying signals, you'd think that when there's large movement, you will need a lot of motor, a large part of the motor cortex. But that's not how it's organized. It's organized by the precisions of the movement, right? By how much we need. So when we need the areas where or organs that need to do really precise manipulations, like the fingers, are represented in huge parts of the brain. And then we still need an amplifier, but the amplifier is the level of the muscles themselves. The muscles themselves are amplifiers. It's related to what I talked about, motor units, right? So a single motor unit can innervate many, many muscles. So we don't need, it's not how much neural power came, but how much single neuron was translated to a lot of power. And the motor cortex is not organized by that. It's organized by the precision, how the amount we need to control actually the movement. And you can see here the nice map that they had in humans, different areas, the tongue, and we have here the face area, and then the arm and the fingers and legs and so on and so forth. Same thing in monkeys, basically. Same idea. It's a nice system now because we can go now and use, because of all these similarities, it's similarity in terms of where it is anatomically, similarities in the way it's organized. This will help us in order to compare between the two, to say, well, we're going to study monkeys. There's high chance that we can generalize it to humans because of all these similarities. So that's the story of the homunculus, of the motor homunculus, as there is for a sensory, for the sensory part. There's a sensory homunculus and also a motor homunculus, and they're tightly related. As we said, in order to control movement precisely, we all the time need to get sensory information. So now the question is, what is the motor cortex doing? And I think I showed this in the introduction, part of this in the introduction. So these are conceptual way we can think about the system. So we can think about any movement that we do as this order of sequences of happening from the stimulus to the response, some sensory motor transformation, and maybe we get some kind of stimulus, look at the world, decide what we want to do, wake up in the morning, and we know we have a class. Should we go or should we not go? We just get we look at the world, and then we need to perceive. We look at the clock. I don't know. We look what is the time, and what does that tell us about when we need to wake up? So there's a perception, and then we need to use this perception for making decisions and doing some kind of making actual intelligent interface about what we perceive, and then that drives the action. We wake up, we go, we brush our teeth, and go to class. And again, this is a reasonable way to think about things, I think, and conceptualize things, but nobody promises this is how the brain actually is organized, right? Nobody says that there are specific areas for action and cognition. Could be that they're organized together. Maybe the same areas that do the action are the same areas that make the decision. Of course, in some sense, it's true. When we think about muscles, we don't think there's cognition in the muscles. We think the muscles are action. But the question is this what's happening at the level of the motor cortex? Or cortex generally? Is the cortex organized along these kind of units? So that's this. And then the action itself, we talked about also, the action itself we can also separate to different parts. We have all what happened before, we should call the intention, what we want to do. It may be the result of the cognition. You can think of it as the result of the decision that we have. And then we talked about this. There's a set of transformation that we need to do. We're looking at the world. We see where our hands. We want to bring our hands to the cup. So we see this in terms of, or we can represent this in terms of the world coordinates of a hand being somewhere and a cup being somewhere. We want to bring this to this. That's one coordinate system. We need to transfer it, for example, to joints, how to move the different parts of the hand. But then we need to translate, and this is called here intrinsic kinematics, the kinematics of the body. And then there's the movement, or here it's called kinetic. Often the name that is used as dynamics or power that we actually need to make, and that's in terms of what activity do we need in the muscle, and that leads to a response. And again, these are different transformations. We can think of this, it's logical to think of this as a system that is linear, that something does one, then there's a different stage that does the other, but it doesn't have to be like that, and it probably is not like that. So these, if we think of these transformations as something that the motor cortex is doing, or the cortex is doing, we would expect some serial processing in terms, as I said, cognition and action, for example, or serial processing in terms of what is the coordination system that is the cortex is doing, the transformation that the cortex is performing. But again, these are intuition. The brain, I know, luckily or not, is much more complicated. And the point is that the brain does not encode single neurons in even a specific area. They're not that the premotor cortex is encoding intrinsic kinematic or extrinsic kinematic, and then the motor cortex, the M1, is encoding only the kinetics, only the dynamics. The things are more complicated, and we see that in many, many areas in the motor structure, we see representation that are complex, that include different parts of this scheme. And also in the higher level, we can see, for example, again, example from the eye movement, we see that the area that controls the eye is also the same area that could make that decisions are making about where to move our eyes. Same area that we see representation even of motivation. All these are happening together in the same cortical area. Again, I'm not saying that this is not this kind of organization does not exist at all. If you push it downwards, I said you can think about the muscles being the actor. That's probably true, but still, it's not that the cortex is organized along these kind of lines. So the question that came, a really important question, and the most basic question in motor cortex, in the motor control, is what does the primary motor cortex do, or what is the activity of single neuron? It tells the other parts of the brain. So, as scientists, I'm sure you're all interested. This seems like, I think, an interesting question, and just answering this question by itself is interesting. But there are also some. But if this is not enough motivation for you, there's also a motivation how this approach can actually help humanity. I'm sure many of you heard about brain-machine interface. I'll show. So the idea. I'll show a movie in a second. So the idea here that we can put some electrodes in the brain of monkeys or humans. I'll show two examples. And then we can use, we put many, many electrodes. This is called a Utah array, an array of, I think, 100 electrodes that are implanted in the motor cortex. We can use this array to get signal, right? We can, for example, identify the spikes. Maybe we can use the local field potential. And then use that in order to extract features from the data. We can use some algorithms to decide how these features are related to a movement of a robot, and that's what you see here, and then send a signal that will actually move a robotic hand. And then the person sees that, and then he can continue and control the world directly through his brainstem. And the idea, of course, is that if you have some lesion in your spinal cord and you cannot move your hands, this will be a way to directly control movement through robots through your brain, because you can't control them any other way.
Is it an idea in humans, or they already do it?
In a second, you'll see the example where they did it. There are many, 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 many technical issues here. Okay, and it's not clear this is the simplest approach for human. For example, you can just look at the eye movements or blinking for making decisions. People do that. Another really nice movie that I saw, very, very impressive, that instead of recording activity directly from the brain, they took the nerve from the spinal cord and rerouted it into the chest of the patient. And then when each time he wanted to move his hand, they were able to record activity in the muscle of the chest, and then they used that activity in order to move a robot. And that's a way. So a lot of the problem that we have here is that there are technical problems. You put these electrodes in time, that signal becomes very bad. We record 100 cells. That's a lot, but still,
It's not 1 million cells, which are probably will be better. And by doing that, they were able to bypass all these limitations, actually use the muscle as a amplifier. And they got very, really nice. You saw that very nice movie. I think I saw it in a TED talk. It's very nice. But this approach, at least the approach of actually recording activity directly from the brain, it has a lot of opportunity because we'll get better in all the technical issues, and we can get much more information from the brain than from just the muscle. And maybe we can have much better controllers in the future. But currently it does work, and here is a movie. I hope it will work this time. So this is also a nice example where I'll tell you what you see. This is also a nice example where a research in monkey has led to possible therapy and even surgery that I'll show you afterwards in humans. So this approach was initially done on monkeys, and here you can see examples. So here you can see a monkey, and this is a robotic hand that is controlling directly through the activity in its brain. His other hand is restrained, and I'll talk about this in a minute. So the experiment puts some kind of food here, and this is the arm that he's controlling. The monkey is supposed to bring this arm here, grasp this thing, and bring it back to his mouth. And this is how it happens. So they put in different areas to show that it's not just, it's a real control. It's not that they just moved in a specific pattern, but he can control it in different places. Okay, and you can go. I'll put this on the web. You can go and look at it. One thing that should, as critical people, should make you a little bit skeptic is that, if you look carefully, he is moving his other hand, right? So the question is, what are we actually doing here? Is it really non-movement at all in monkeys? For sure, it's not the same movement. It's not that he's moving his hand in order to grasp it, but we're decoding activity from the motor cortex that maybe is also moving other muscles in order to get to this. In a second, I'll show you an example in humans where he cannot move his hands at all.
It's a problem because I don't understand why it's a problem. Because we kind of understand. Okay, maybe.
Okay, so the question: what is the monkey doing? Right? Is he learning some abstract mapping that is not related at all to the muscles? Or is he using some different kind of pattern of activation of the muscles to do this task? These are two different things. So you can think of even moving a mouse, right, as some arbitrary transformation, right? And our ancestors didn't have mouse, and they have different kind of mice. They didn't have a mouse to move on a screen, right? So you have this arbitrary transformation which you use your muscles in order to implement. That could be one possibility. The other possibility, you're not moving your muscles at all, right? The brain learned somehow to do this kind of task. And in monkeys' experiments, you can do some controls, but it's hard to really get 100% convinced that he's not using it all his muscle. It's not critical in terms of I would call engineering a sense, because what we want to do is use some arbitrary transformation that the brain is learning in order to decode it. So in that sense, it's the same. In sense of the interpretation of what's really happening in the muscle, it's a little bit different. So that's a monkey example. And here's the human example. So after they did this with monkeys, they got approved to do it with human subjects. Show you. There's no voice. Okay. So this person is you can see has a stroke or a spinal cord injury. You can see here the recording device. The electrode is implanted in the brain, and then this is a connector that connects to the device. Here you can see the experiment or whatever, the doctor in this case, that is controlling it's not controlling the harm, but is monitoring the activity. And here you can see how after. So there's a process where you need to train the person, right? Because You don't know, right? You can tell them, imagine you're moving your hand or things like that, and then they do it, and then you use that information in order to try to decode the activity. You don't know that just when you put your electrodes. You need somehow, it's a iterative process where you tell something, the person to do something, and then he can do it. You decode that activity, and then you see how good you are, and both the algorithms are getting better, and also the human is getting better. So they're teaching each other, the computer and the person, in this case. And here is what you get after some time. So she's controlling the robot, and she's able to drink. And she's very happy. So this is a person that can't move it all his hands, but still using this, she's so happy. He's so happy. Everybody's happy. Yes.
How long is this process of learning?
I don't know exactly, but part of the challenge is to make it as short as possible, right, and intuitive as possible. So one of the reasons for choosing, well, you can do this in any area in the brain. You don't have to put it in the motor cortex, right? You can put electrodes in probably the parietal cortex, right, and do the same kind of thing, and just learn. The person will learn somehow to control his neuron in order to do a movement. The reason the motor cortex was at least initially the most intuitive place is because we have some idea of what's going on. So it made it easier to, in some sense, to actually control an arm movement. But it really depends on the details of the case. I don't know the exact answer. Okay, so that's the end point of what I'm going to talk in the next 2 hours and a half. The end point of what we got from being able to monitor activity in M1. And what I want to talk now is what is actually M1 coding. So the first research was that actually recorded activity in M1 was done by Everts in 1968. He actually started. It was so what you need to do to do this is to get an animal awake and record the activity. And the techniques for doing that developed in 1960s. So Everts was one of the pioneers of this field. He was initially interested in sleep. So he had monkeys sleep, but then he figured out that he actually can see actually more interpretable activity like movements. And then he became really the pioneer of measuring activity while monkeys behave. At the same time, there were other people that were recording in somatosensory. Vernon Mountcastle, if you heard the name, he was the pioneer in the sensory areas and the parietal areas. And there were a bunch of people that were doing recording in eye movements areas. Bob Wirtz, if you heard the name. They really I would say the grandfathers of me, maybe great grandfathers of you. The pioneers of this field. So the idea is to put an electrode in the motor cortex next to a cell. The motor cortex, I didn't talk about it, but the motor cortex has one of the largest cells in the brain, the cells that in the pyramidal tract. They're huge cells, and you can get the signals relatively easy with extracellular activity. And so here you can see where he recorded, and here you can see what the monkey was doing. The monkey was simply doing this kind of movement. Flexing and extension is the wrist. And here you can see the activity, the extracellular activity of a neuron. And you can see it firing, then doing nothing, and then the arm goes down, still doing nothing. And then before the arm starts going up, the wrist is starting going up, you see this activity, and during the movement you see this strong activity, right, of the neuron. And then you get again to the next cycle, and then see nothing, and so on. And this is one movement, and another movement, very reproducible, and then another movement. So a few comments. First, you see that even before the arm starts to move, the wrist starts to move, you see activity. Two interpretations for this. One is that even before you see the kinematics of the movement, even before the arm actually moves, there is a EMG that's starting before. That's one point. So the EMG precedes the arm movement. And another thing more is that activity in the motor cortex is not just directly related to movement, it's also related to the planning of the movement, the preparation for the movement. So that could be another interpretation for this kind of activity, why it's happening so much before. But nevertheless, this is a nice, very nice neuron that's strong, really, really strong, that fires really, really strongly during the movement, during the extension of the movement of the wrist. So the question, what is this related to? It could be, is it related to the kinematics of the movement, the arm moving up and down, or is it related actually to the power, the muscle power that the monkey is, the power that the monkey is doing? So for this is maybe one of the nicest and really fundamental experiments in motor cortex. Everts came with this kind of experiment. And the idea is to ask, what are the neurons in the motor cortex coding? So let's look at the different things. So we had a monkey sitting in a chair in front of this handle, holding this handle, and while he was doing this, he recorded activity in the motor cortex in M1. Okay. And this is the condition, this is in a sense the control condition, where there's no load. In a second I'll show you what was the load. In this case, he's just moving his arm in one direction, and you can see it here. He's flexing, he's moving his arm like this. So there's an extension, then he's flexing his arm, and then the arm is flexed. And you can see the time of the movement, you can see the activity in the muscle. So this is EMG. This is the overall activity in the overall electric activity of the muscle. You just put an electrode you put an electrode on the muscle. You record the overall activity. It's like, in a sense, it's like the LFP of the muscle. And you see that initially the flexor was not active. Then at one point it started to be active. And you see here the movement. Okay. The extensor, you see the opposite pattern, right? And then it becomes quiet. And then we recorded a neuron similar to the neuron that we saw before. There was a activity before, and a little bit during the movement in this case, and then some more activity later while the arm is flexed. This is the same condition that we saw before. And just from this, it's hard to say, is it related to the power or the location of the arm? Is it related to the extension, flexion, or the actual muscle? So then what he did is this manipulation. He added loads. So what you see here is the same device, but now we added a load. Here you see this weight represents a load, and now he's doing the same behavior. He's doing, again, from extension to flexor, but in order to do this behavior, he needs a lot more force. Is that clear? Yes? No? Maybe? Okay. So now the kinematics is the same. He's doing the same kind of behavior, but the powers are different. And in this case, what he found is that there's much more activity. So first, let's look at the muscles. There's already flexion before, because he needs to, this is against the power of the weight. So the flexor is already active. Even before, there's some fire rate, as opposed to before there was no firing rate. And then during the movement, you see much more force, and again, much more activity of the neuron. So you can see here, on the other hand, the flexor, the extensor was not activated at all in this case. And you see that this neuron really followed the power and didn't follow just the kinematics. So this activity here above is much smaller than this activity. So that's one condition. And you can do also the symmetric condition, where you put the load on the other side. And that's what he did. So now he's doing the movement, and the load is actually helping him, right? So so before, he doesn't need the flexor was not activated at all. In fact, he was activating the extensor, because otherwise the hand will already move before it's supposed to move. And then during the movement, basically what he's doing during this movement is releasing, right? He's not going against the power of the load. He's just letting the load move it. And that's what you see here. During the movement itself, it's just no power. All the movement is caused by the weight. And in this case, this neuron doesn't fire at all. So we have here again the kinematics is very similar in all three conditions. The way the arm moves, or the profile of the arm moves, is very, very similar. But the firing rate is very, very different, because the powers are different. So these kind of experiments, and these are pioneering experiments, show that actually the activity in the frontal cortex is related to the muscle. is related to the muscle activity and not the kinematics of the arm. So a few comments about this. First, these were not all the neurons. There were some other neurons that didn't follow the dynamics. I think he said something like 50% were in his experiment related to the power, to the dynamics of the movement. Others were not. And that, so it still, it didn't solve the problem, but it did say that some neurons in the motor cortex code power. And for him, when you read his paper, he said this was a surprise. At least he wrote in the paper. I'm not sure, how much it was really a surprise. But that he claims that the hypothesis that he had before this was that the activity was actually related, would not be related to the power. So the motor cortex is more abstract in the sense that it's controlling maybe the direction of movement, but not the actual powers themselves. Again, this is all before we showed that a single neuron is connected directly to the motor pathways. This is all before that. Now we know that that the motor cortex could control the power directly. At that point, it was for him at least, the way he presented it is somewhat of a surprise. So that's Everts. That's classical experiment of Everts. And then for a long time, this was mostly the leading paradigm, leading consensus in the field. And then came in 1982, Georgopoulos, and tried a slightly different experiment. And in terms of sociology of science, this is interesting because Everts did a very really controlled experiment where he controlled the power and looked at movement. Georgopoulos decided to do a less controlled experiment where he did not control the powers. He just told the monkey to move his arm in 8 different directions. So this is the experiment. He's standing in front of this screen. It's supposed to move of 1 direction, I think, visually cued somehow. And here you can see the arm movement, the movement of the endpoint of the manipulandum. Quite straight, nice movements. Some not as straight, but this is the classical way of looking at this data. And then he recorded activity. And what he found is 2 things. First, he found that cells have a preferred direction. This is not surprising. Also, if it was, regardless of what I talked before, you can get preferred direction also from the muscle activity. So what you see here are the rasters in the 8 different directions. Time 0 is time when the arm started to move. Okay, so this is each line is a one trial. Each dot is a spike, and you can see here in this direction, you can see a lot of activity, and also in this direction, maybe this direction a little bit less, maybe this direction even less, and then in this direction there's no firing rate during the movement itself. So you can look now at the function of the direction of the firing rate, and you can fit this, for example, as a cosine fit tuning, as most of you have seen before, and get the tuning curve of the cell, the cosine tuning curve of the cell. And so this is one cell. And what Georgopoulos said, well, we have this information from one cell. How do we combine this information across many, many, many cells? And his idea is that we can use different cells, the preferred direction, the activity of different cells, in order to pool them across all the activity. And the idea is that you have a cell, and this cell has a preferred direction, and the amount of firing of each cell will tell you, in a sense, how much this cell is pulling towards this direction. So the analogy here is we have 2 groups. Each let's say you have only 2 directions. Each person here is a neuron, right? And the amount of sweat or the amount that is pulling is how much the cell is firing. So we have these cells where their preferred direction is to the right. When they fire really, really strongly, they pull towards this direction. On the other hand, we have another group that pulls towards this direction, and the overall movement will be decided by how much is pulled toward the sum of all the pulling of the neurons. And so you can imagine that if all this group is pulling really, really strong, and this group is doing nothing, the movement of the rope will be in this direction. So that's the idea of the model. I'll go into details more in a second. So each cell has a preferred direction. The amount you pull, and this is now in circular mathematics, so it's not just 2 directions, across all 360 degrees. And the strength of how much you pull depends on the firing rate of the cell, right? So that's why I said that you can think of the firing rate as the amount of sweat this person has. Another thing that you can have in this model, so you can think of so different cells have different baseline firing rate. So you can actually decrease your firing rate. And you can think of that as different than this, that these people can actually pull towards the other direction, or push in a sense. So it's not a rope, but a metal rod, I don't know, something like that, that they can help these people. So firing rate beneath baseline could be actually add to the force in the other direction. And what this mathematically is not very complicated math, but this means that each cell is a directional vector, and the amount of firing is the length of the vector. And now you just have many vectors. Each cell is a vector. You sum all these vectors, and you get the population vectors. And the population vector, what Georgopoulos showed, was a very good prediction of the actual movement of the monkey. So in terms of math, maybe before. That will be before. Next time I'll give you an example. In terms of math, so we have here, this is the output, the population vector. So this is a vector. We have here, each cell has a preferred direction. I is just the index of the neuron. And this WI, and it has also a specific time, right, will be proportional to the? Exactly. Okay, and then you have simply a different firing rates. You have different weighting of the preferred direction. So pi is the preferred direction. And the small index here is for time t. That means we can have different firing rate is something that modulated in time. And initially, Georgopoulos did not do this; just looked at whole segments of time. But then you can do this, and I'll show maybe next time a picture how you can actually look at the population vector across time. When you have complex movement, that's really how it follows nicely the movement. And as I said, the weight is the firing rate minus the baseline firing rate. So you can have that minus, this could be negative, right? And that will actually contribute to movement in the other direction. But most of the cells, at least in the border cortex, don't have very high firing rate. They can mainly increase their firing rate. It's hard for them to decrease their firing rate. So that's the vector. Maybe we have time for just a very simple example how this works. This is not as complex as neural networks 1 and 2, but still a simple example for how this works. So this is the equation. So now imagine you have only 4 neurons in your brain that have 4 different preferred directions, 0, 9, 180, and 270 degrees. And we have some kind, so this is a vector representation of this, right, of the 4 different directions. And now the different cells have, let's say the arm is moving now to the right, or these cells are causing the arm to move to the right. So let's say they modulate their firing rate. So cell number 1, the arm is moving to the right, so 0 degrees is to the right in my convention, 90 is up, 180 left, and 270 down. So cell number 1 is firing strongly, because changing the firing rate strongly because of the monkey wants to move to or human wants to move to the right. Cell number 2 maybe still is increasing its firing rate, but not as much because it's not his preferred direction. Maybe cell in the opposite will decrease their firing rate a little bit, and cell number 4, like cell number 2, will increase a little bit the firing rate, and then you want to calculate the vector. So you sum. One way to do it is sum the x, the horizontal and the vertical, the components separately. So in this case, you have the x is 10. You multiply it by 1, just this number times this number, and then 5 numbers and then times 0, and so on and so forth, and you get the number 12. And then when you do the same thing for y, you get the number 0. Okay. So the vector, the population vector here has a value of 12 and 0, which is good because it's to the right, right? And another thing to notice is that these values, right, it could be 12, 0, but it could be 100, 0. And the amount that you get here, the size of the vector will tell you, the direction will tell you the direction of movement, and the size will tell you how much to move in that direction. So if it's moving faster, to move just, we'll expect here larger responses. So that's the example. So we get the population vector is 12, 0. It has a direction and has a amplitude that will tell you the direction and amplitude of movement. A really simple idea, almost very naive idea. Because it's so simple, It's still with us even after 30 years or even more. But first, what Georgopoulos showed that it really captures the data his data, the direction of the movement of the monkey. So here you can see an example for that. So these are movements in 8 different directions. Each line here is one neuron. Okay. The size of the length of the line is proportional to the firing rate of the neuron of each black line. The direction is aligned based the preferred direction. So cells that are in the lines that are in this direction are cells with a preferred direction of 90 degrees up in this case. And so you have many different cells. You do the same mathematics that I showed you before, and you get this red line. This is the population vector. And you can see very nicely that in movements to the up, you get a population vector up, and so in all different directions, you get, and it really follows the direction of the movement, right? The vector was in the direction of the movement, in the actual direction of the movement. There are small differences, but again, even if you think this is the only thing that happens, you can still expect tiny differences, maybe because the arm is not moving completely straight. But I want to show next time. I'll show a bit more of this. But this is really strong contrast to what Everett said, right? This is ignoring any muscle activity. It's taking only the kinematics, only the direction of the arm, and saying, let's see if we can extract that information from the motor cortex. And the answer is yes. It doesn't tell us how the brain uses or how the motor cortex uses this information. It doesn't even tell us that this is the connection, this is what is connected to the muscle. It just tells us that the information about the kinematics is in the motor cortex. Okay? And that's the conclusion from this. And next time we'll continue to talk about this and more controls and more nice experiment about the coding of the cells in the motor cortex. And remember this will also be relevant for the talks of the students. Good luck.
טוב, יש תשובות טריוויאליות, אבל אני לא משכנע אותך שיש רעש בזה, כן? נוירונים מאוד מאוד רועשים, וצריך הרבה. אבל כמה נראה? 100. הנקודה היא שאפילו עם 100 תאים, זה מצליח לקבל, כן, אין רק 100 תאים במובן, אבל אפילו עם 100 תאים, אתה מקבל בברין משין אינטרפירס, תוצאות די טובות, או גם בפופוליישן. אז יש את האינפורמציה הזאת גם ב-100. השאלה זה למה זה חוכם. זו שאלה טובה, אני תשובה. יש כל מיני תשובות עוד דוגמאות כאלה, ששמות תשובות של תנועה, יש סיפור מורכבת, כן, אבל אני בטוח שנגעו מיליון תאים את המסתדר, כן. שאלה טובה. מיטב ידידי מיטוב.
בעצם ששם נמצא.
כן. שם, הנה עוד מימד, אתה רוצה קח עוד 4 למימד, עדיין לא. כן, השלב ממדים של תנועה במרחב. בשרירים זה, אתה יודע, זה הרבה יותר מורכב. כן, שואל גם ממדים של השרירים, שזה משהו אחר. What makes us human, ככה נקרא הכנס?
אני אגיד לך אבל מה אני חושבת?
אתה מגיע כאילו לכנס?
אני אגיע כן, אבל אני חושב שאולי לפני. אני לא מגיע, אבל אני מגיע לא בבוקר.
אני אגיד לך אבל מה אני חושבת? שיכול להיות שהם פינים את העמוד האחרון, אבל הם לא התכוונו שתקראי נגיד לא יודעת. כאילו שזה לפעמים נניח משהו כזה.
אבל אני לא יודעת.
אנחנו לא יודעים. באמת, זה ככה נראה לי.
Development of human skills, זה חשוב?
PR זה זמן החזרה שעובר בין תחילתה של...
הכל חשוב? לא, הנה, diet, tool use and teaching, chimpanzees and human skills, נשמע מעניין. בוא נראה מה לפני כן. טוב, זה ב...
אני פשוט חושבת שגם PR וגם PR וגם... מה זה PR?
זה ב3:30. מה יש בשתיים?
אנחנו בכללי, מה זה PR? מה
Massively parallel dissection of human accelerated regions.
זה קשור לזה?
זה נראה קצת ממש מושקע, נכון?
כן.
לביאת ההרפאה.
זה שיש להם אתר.
כן, ואתה? לא מבין לראות מאוד מושקעות.
Human accelerated regions.
הוא האמת נכון, הנחתי שלא יהיו לי
ג'נומי. טוב, אז אפשר להיפגש ב... זה לא בא לי. אתם צריכים ללכת לזה, או אני לא רוצה לגזול לכם את ה...
לא, להפך, אין לנו מקום.
מה, אתם לא יכולים לבוא?
כאילו, טוענים שלא. אני אגיד הספקתי להירשם רק ליום השלישי.
אני אבוא, אם לא יתנו להיכנס. אני לא רוצה אותם. אני לא מוכן להיות במקום שלא... הפוך מזה.
אני כבר פה, אז אני צריכה לבוא. כן, אני אנסה בכל מקרה.
וואלה, לא הייתי כלום.
3. אפשר כן. יום שני כמה זמן אנחנו צריכים? 2:30?
רצינו לעבור איתך על מבנה של המצגת, אבל יש לנו פחות או יותר, וגם יש לנו כמה שאלות, אז אנחנו יכולים לשלוח לך במייל את השאלות.
תשלחו לי לפני,
אוקיי.
אז אני יודע מה זה יעזור לי. אז נגיד 2:30?
ואם כן, אז משהו יותר כללי כזה, שנגיד שעה 2 תחשוב שהוא יותר רגיש, או מי יותר רגיש?
אז 2:30?
2:30 בסדר, וזה לנו שעה.
מעולה.
אנחנו להיכנס.
אז ניפגש פה?
אין פה איזשהו שיעור טוב נוסף. תשלחו לי שאלות, אני אחזור לשתף לכולם.
יש שאלה
כן, כן.
יש לי בראש, יש גם עניין של שחרור. אנחנו נראה כדי כזה לבחור מה היה כאילו אם יש כמה...
גרתי לסיסטם קשור לקשר.
כמה אפשרויות כאילו מתחרות, כאילו נוירונים שונים שהם אחראים לכיוונים שונים כמו קוד, ואז בסוף כיוון אחד צריך להיבחר.
הבנתי, לעשות כזה ספוטלייט על הזה.
כן, שכאילו שזה יהיה לא ברמת שהמשקול לא יהיה חלקי או רק לפי קטגוריה, גם יהיה
הקצב יכול לייצג אחרי הספוטלייט. זאת אומרת שאני מפעיל את הכל, ואז יש איזשהו ספוטלייט
שקצב ירידת
שזה התוצאה שלו, כן. ואת אומרת, אני לא יודע מה נכון. ואת יודעת, קשב של פרונטל-אייפיל למשל, זה שני אזורים משונה. זה כזה שהפרונטל-אייפיל זה האזור היחידי שאנחנו עושים בקורטקס שבאמת עושים את העיניים, וגם בו חוקרים דברים סנסוריים. וגם בו רוב האנשים חוקרים דברים סנסוריים. אז זאת אומרת, אז מה המודל? זאת אומרת שהבחירה תהיה הספוטלייט? מה את מנסה להסביר?
אני לא יודעת ספוטלייט, כאילו לא יודעת איזה הנהלה, אבל שכאילו איכשהו על ידי, לא דווקא על ידי קצב ירין, אבל על ידי זה שכאילו תהיה יותר מסונכרנת. אז זה מה שכאילו שיגרום לכיוון מסוים להיבחר, כאילו זה מה שייתן את המשקולות.
כן, כן. אז סנכרון זה אפשר להסתכל, לרשום שני תאים לראות אם יותר מסונכרנים בזמן תנועה. שיש עלייה בסנכרון אולי בהקטנה, זה לא הרבה.
כי מהטוב לא
לא צריך. כן, זה רק להסביר זה, עכשיו זה אפשר לעשות ניסוי שאתה מסתכל על שני תאים במקביל, כן, לשאול האם במהלך תנועה יכולת שם הם יותר מסונכרנים. זה עדין, כי נגיד, נגיד שכל התאים לכיוון המוצע וזה יוריד את הגבוה, אז באמת מצפה מהמודל הפשוט הזה שיזוז, שזה כן, יותר סיכוי שפשוט יזוז יותר מהר למשל, יש קשר בין הסנכרון לבין ההתנהגות. אז השאלה זה לא רק הסנכרון, אם זה יותר מהדבר הזה. והתשובה היא אולי קצת. זה בטח לא הדבר העיקרי שקורה. סנכרון במוח זה ברור, כי הוא קיים, והיא לא במובן פונקציונלי, איזה מובן. את חושבת בכלל על מנגנונים של סנכרון, של אוסילציות כאלה שהסתנכרנו בשביל...
כן,
האמת שתשמעי את המאמר של השני. כן, כן. כי שם מדברים כאילו על אוסילציות. אז אולי שם זה יכול להיות. כאילו מה הייתי?
כי יש לך חלקים שהוא יותר...
כן, אמרתם שאתם יכולים לוותר על השקף האחד הזה שקשור אליו. לדעתי.
כאילו על ה... כן. זהו, אנחנו נתנו לעצמנו על להסביר את זה.
כן, כן. אני אומרת, לדעתי אפשר גם בלי להסביר את המאמר, בלי השקף הזה. בכלל להסביר את זה.
אנחנו כן הכנסנו.
ניתן, אוקיי.
כי זה היה נראה...
המחשבה הייתה להסביר את זה יותר בכיוון של אינטואיציה בכמה משפטים של למה אסור ולא בדיוק האיך אסור.
כן, 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 כן. אז מוסי היה לפניכם.
זהו, אז כאילו צריך ממש בכמה משפטים רק להסביר את הקונספט ולא להעמיק.
אבל למה לך?
תראה שזה לא מספיק.
כן.
ניסו לעשות הקטע הזה עם היד הרובוטית גם על אנשים שעולם לא הייתה להם יד.
אבל צריכה סיבה טובה, לא יודע. קודם כל לא יודע. לא כל כך פשוט לקבל אישור, כן. צריכה להשתיל אלקטרוד על בן אדם. אני גם לא חושב שאני לא מכיר שאפשר לעשות את הרופאים בתור כן, כי הוא לא בטוח שכן, אדם שידע את זה, אז יש לו, אני חושב, המנגנונים עוד שם, המושג של כיוון בקורטקס, למשל, יש שם.
אדם שפעם לא השתמש,
יש המון קצת.
שהמנגנונים האלה נכתבו לטובת משהו אחר.
אני אומרת, לא יכולים להביא בקורטקס, במות או קורטקס, בכל מקום. וזה תהליך של למידה, שהבן אדם, יש לך איזשהו אינטנשן, יש לך איזשהו אלגוריתם שמנסה לקרוא את האינטנשן הזה. אתה יכול להתחיל נגיד על לדמיין כיוונים שלפעמים אפשר לעשות, ואז לסמך זה לעשות את הדיקודים, ואז להשתפר, אז הבן אדם עושה איזושהי תנועה ומנסה ללמוד איך לעשות אותה יותר טוב. כל הזמן הבן אדם לומד על אותם אלגוריתמים,